Okay, so in this video, we're going to continue talking about Unit 2. This is going to be the second part of that. It's going to be capacitors. Um, and so the first thing we're going to do is really talk about some of this general information, just do some simple calculations, and then we'll get into this whole E field versus potential difference of a capacitor. So the first thing is that a capacitor, right, consists of two isolated conductors, usually plates, okay, with charges positive Q and negative Q, and it transforms electric potential energy. So one thing to note is that one plate will be positively charged and one plate will be negatively charged. Okay, I think in the diagram I have them kind of um, flipped backwards, but that's how a capacitor works, right? And so you have to remember, if we're talking about E field, it goes from positive to negative, right? It's throughout this entire capacitor. Um, and what they really do is they store energy, okay, for use later. One of the big kind of real world examples of a capacitor is the defibrillator that are used in medical, right? And so when you watch a show, or if hopefully you've never experienced this, but they say clear because it's charging because they don't want it to discharge, right? And so what it does is it stores energy until they hit the buttons, and then it discharges, right? So now in schools and offices, they have what are called AEDs, right? And AED is one of those defibrillators. It's just does it all for the person, right? And so they don't have to do the whole charging thing. It charges itself and then it releases it. But we'll get more into that aspect of it when we talk about circuits. But that's just where capacitors are used kind of in the real world. Right. So it does have something called capacitance. All right. So its capacitance is defined from the equation Q equals CV, right? Or sometimes you see this as C equals Q over V. All right. And remember, V is the potential difference, right, between the plates. And typically it'll say like it's charged with a 12-volt battery, right? And so the it takes the voltage of the battery and so forth. C is the capacitance, right? And the way you think about capacitance is it's like, the capacity of a bucket, right? Because you see here's the word capacity, right? And you see that kind of that root word, if you want to say, of capacit, right? And so it's like how much can this object hold, right? This device, okay? It's measured in farads, right? And farads are named after Michael Faraday, who did research on electromagnetic induction. And so a farad, right, is a coulomb per volt, right? And so it's the amount of charge per volt that is given to it. Okay. Now, a capacitor will be charged, right? And how do we charge it? Well, we place it in an electric circuit with a battery. Okay. And so the voltage from the battery charges, stores that capacitance into the capacitor until it's ready to be used. And that's how the defibrillators work. So once it says that it's charging, that's what it means, is that it's connected to the power source and that it's getting ready to be discharged. And it's not discharged until you hit the buttons on the paddles. Okay. And so when plates are uncharged, the potential difference between them is zero. And so as the plates become oppositely charged, right? So one's positive, one's negative, the potential difference increases until it's equal to the potential difference between the terminals of the battery, right? And so it's going to continue to move. And then what you can do is you can find the capacitor, you can find, or excuse me, you can find the capacitance, you can find the charge stored, and so forth. Okay, so here's just a quick little example. It says, does the capacitance of a capacitor increase, decrease, or remain the same when the charge Q on it is doubled, and B, when the potential difference across it is tripled? Okay, so this is basically one of those factors of one problem. So we say Q equals CV. So we're doubling the Q, trying to determine the C, but we're saying that the voltage will stay the same. Okay. And so what happens when you double the the charge? Well, the capacitance doubles as well. So this one, in this situation, it will increase. Okay. What happens is Q and C are directly proportional. Okay. And then you also see that Q and V are also directly proportional, right? So the more charge, the more capacitance. The more charge, the greater the voltage or the potential difference. Okay, so let's look at the second part. What happens when the potential difference is tripled? So again, we start with Q equals CV. So we're going to keep the charge the same. Okay, we're going to we're going to find the capacitance, and we're tripling the potential difference. And so for us to solve for C, we need to divide by 3, and it tells us that this, for a case when you increase the voltage difference, right, you're going to decrease the capacitance. Okay, and the way to think about it is, if I had like a, say, a bucket of water, right? Okay, and so think about my Q is the water that I put in, right? My V, right, will be kind of like my volume, right? And so the more water I put in, the more that this can hold, right? If I decrease the, sorry, I got that backwards. We'll scratch that. We'll come back to that at a later video or later part. Okay. I didn't think that through. Okay. Now, capacitance also does depend on the distance between them, and that's really focused around what are called parallate parallel plate capacitors. With the purple pen. So a parallel plate capacitor, and generally this is, the capacitors that we do use. Okay, there's a simple device that you can use in a classroom called a Leyden jar, right? And so this is what happens. Okay, but right now the gap between our, I forgot to put so C and V have an inverse relationship. Okay. Um, and so if I increase one, I decrease the other, right? And so um, a Leyden jar. So right now, all of our capacitors are going to be filled with air. We'll get into what are called dielectrics, which is the last part of this unit, where the gap between the plates is something other than air. So right now we're looking at air. Okay, and so the capacitance of a parallel plate capacitor can be determined by using the formula epsilon naught times the area divided by the distance. And if you think about it, right, so we've got these plates that are negative or positively charged and negatively charged. They're going to have an area, right, and they're going to be separated by a distance d. Okay, so that distance between them also does matter. So notice if I increase the distance between them, right, C and D have an uh, okay, so they have not an inverse relationship. Apologize. They have a direct relationship. Okay. So if I increase the distance between them, I increase the capacitance. If I decrease the distance between them, I decrease the capacitance. Okay. And you can see that area has an inverse relationship. So if I decrease the area, right, I increase the capacitance, right? And so remember, this epsilon naught, again, is that permittivity constant. Permittivity constant, and it has a value of 8.85 times 10 to the negative 12th farads per meter. Okay. Um, and so, again, this is just a standard that's given to you on the AP Physics C formula chart. Okay. So let's look at um, let's look at an example. This is a parallel plate capacitor, has circular plates of 8.20 centimeter radius that are separated by 1.3 millimeters. Okay. So they tell us that we have, and your plates don't have to be rectangular. And so it tells us as a radius, sorry about that, a radius of 8.20 centimeters, which we would have to convert to meters. So it'd be 8.20 times 10 to the negative 2 meters, right? And they're separated by a distance of 1.30 millimeters, which we need to convert to meters, which is 1.30 times 10 to the negative 3 meters. Okay, so we're going to find first the capacitance, and then second the charge if there's a potential difference of 120 volts. Okay, and so we just use our C equals epsilon naught A over D, right? And so we're going to use epsilon naught times pi r squared, because it's the area of a circle, divided by the distance. And so it's going to be 8.85 times 10 to the negative 12th times pi, right, times the radius, so 8.20 times 10 to the negative 2 meters squared over 1.30 times 10 to the negative 3 meters. Put that into our calculator, and we get a capacitance of 1.44 times 10 to the negative 10th farads, or 144 picofarads. Okay, and so that's part A, the capacitance. And then for part B, we're just going to use Q equals CV, right, to find the charge. So we're going to take that number we just found, 1.44 times 10 to the negative 10th, and we're going to multiply that by 120. And this will give us the amount of charge that is stored on the um, in the capacitor. So that's going to be 1.73 times 10 to the negative 8th coulombs. Okay, so I'm going to split this video up so we're not kind of like dragging this out, because the next problems are, now we're going to bring in the calculus piece into this, where we're going to revisit Gauss's law.